Greetings, chemists. The last time, in the last video, we talked about why an atom might radioactively decay by spitting out a piece of itself. So if we had a bunch of atoms in a sample, let's say these are all atomic nuclei, and I probably would have to draw them much bigger than this, although there are small nuclei that are unstable as well. And suppose they're all sitting here, and that the kind of nucleus I have drawn is an unstable nucleus. It has the wrong ratio of protons to neutrons to hold itself together. And so you can picture them jiggling around with too much energy. Eventually, one of them will decay spontaneously. And there's no way to predict when a single one will finally decay. But at some point in time, one of them will decay by shooting out a piece of itself, and then it will become, hopefully, more stable. Eventually, it will have decayed and become more stable. And then these are all still jiggling around with all this extra energy, and eventually one more of them will go, etc. And what we're going to look at today is the rate at which that occurs. Okay? So if we were to look at all of the atoms in this sample, and consider a sample that has moles of atoms, lots and lots of atoms, okay? And we were to measure over time the mass of that sample. Let's suppose the vertical axis is mass, and the horizontal axis is how much time it has passed, because you wait a little bit, you wait, you're watching, and then at some point in time, one of these things decays, okay? So over time, what you would see is this, that at the very beginning, the rate of decay is very large, and as time goes on, that slope flattens out, and you get a curve like this. So very many atoms are changing very quickly at the beginning, and at the end, they are not changing very quickly at all. This is an inverse exponential curve, a 1 over e curve, if you will. And one of the peculiarities of a 1 over e curve is it has something we call a time constant. Okay? And a time constant means that if you were to go, let's say, a certain amount of time, let's say that's t1, you would lose a certain fraction of the sample. If you were to go the same amount of time again over here, let's say that time interval to t2 is the same amount of time as the time interval to t1, you would lose the same fraction of the overall sample. So for instance, let's say that when I went from time 0 to time 1, that represents me losing 1/3 of the mass. When I go from time 1 to time 2, I lose 1/3 again. But it's not exactly, I'll point out why that may be a confusing statement to make. All right, and in fact, let's not talk about a third, let's talk about a half. Let's suppose that I start off with some uranium, and that let's say that this type of uranium that I have picked had 20 grams of uranium in it. And I wait a certain amount of time. Let's say I wait 5 minutes, and I measure my uranium again to see how much of it is left. What I would find is that, well, let's suppose that I find that there are 10 grams of uranium that are still there. Half of it. Now I wait another 5 minutes. Well, you might expect, oh, it's going to lose the rest of it, right? But that's not what we see. We see the rate slow down. In fact, what we lose is half of the rest of it again. And now I'm left with 5 grams of uranium. And if I wait another 5 minutes, 5 more minutes, now when I look, there will only be 2.5 grams of uranium. What we see then is that every time the 5 minutes goes by, I lose half of what I have, not half of what I started with, but half of what I now have, and half of what I now have, and half of what I now have. And that's just because there's no real prediction of when each of these atoms is going to go, but as a statistical event, they are falling apart at an inverse exponential rate. So this time, this 5 minutes seems to be significant. For whatever sample of uranium I picked, I know that specific type of uranium decreases by half every 5 minutes. So what we say is, we define a term. There's a time, and I'll call it time 1/2. I'll put a little 1/2 at the bottom there to let you know that's what I mean, is the time it takes for half of the atoms in a sample to decay and turn into something else, right? If it was an alpha emitter, if this was a uranium alpha emitter, it would be turning into thorium. It wouldn't be disappearing. I would just lose 10 grams of uranium and maybe gain 10 grams of thorium, right? But it would no longer be uranium. It would have decayed. We call this T1/2, it has a name, is the half-life, for obvious reasons. Okay? So, if you want, there is an equation. You could say that the mass as a function of time for some radioactive sample would be equal to the starting mass. I'll put a 0 there to indicate time 0, right? That's how much I started with. The starting mass times whatever the half-life is to the power of n. And n is how many half-lives have gone by. So n equals number of half-lives. To give you an example, up here, when I went from 20 grams to 10 grams, I had a half-life of 5 minutes, okay? When I go from 20 grams to, from 20 to 10 took 5 minutes, from 20 to 5 took 5, and 5 took 10 minutes. That's 2 half-lives. So if I was going to calculate how long after 2 half-lives, I would put n equals 2 for that equation. So how is this useful? Well, let's take a reaction that happens in the atmosphere. Okay, in the atmosphere, there's a bunch of gases. There's nitrogen is most of the atmosphere. That's like 80% of the atmosphere. There's oxygen, which is like 19.5 or something. It's almost 20% of the atmosphere. And then there's that extra 1% is some other things, but CO2 is down there. CO2 is not 1%, but it's a fraction there. There's a lot of this in the atmosphere. And it turns out it's going up. Well, that includes a carbon atom. That carbon atom has 6 electrons or 6 protons and 6 neutrons. So that carbon atom is got 12 mass. But while that CO2, here's the CO2 atom, is floating around in the air, there's sunlight coming in. And that sunlight sometimes has the power, right? Like UV rays or higher energy rays, has sometimes the power to cause changes in that nucleus and to turn it into not carbon-12, but carbon-14. Now, that happens at a certain rate. And so you can actually go out and capture a sample of the air. And if you look at the carbon in the air, I don't care about the oxygens for this, let's just focus on the carbon, you will see mostly these, because this doesn't happen as quickly or very quickly at all. You'll see mostly, I think it's like 99% or 98% or so, carbon-12. You will see a little bit of carbon-13, and you will see a tiny fraction, a very tiny fraction of carbon-14. Carbon-14 has 8 neutrons instead of 6. And in various molecules. So some of the CO2s will have carbon-12, some of them will have C13, etc. Well, that CO2 molecule, that's what plants use to grow. So you'll have a plant. Here's my plant. Don't judge my plant. Okay, growing in the ground and absorbing those CO2s and using them to form sugars. Okay, breathing them in, you could say. And now the carbons that make up the structure in the plant are some 12s and some 13s and some 14s in about the same ratio, right? If you had 99% here and like 0.9% here and 1% of this, if that was the composition in the atmosphere, then that's probably going to be the same composition as the plant, because those are the pieces the plant can suck out of the air and turn into its own structures. We eat the plants, right? So the sugar that's in the plant, right, we extract that, we put it in our coffee, we flavor our cookies with it, whatever. So the carbon in our bodies is probably also of a similar ratio of 99.9 and 0.1%. And you're also constantly replacing it, right? So every time you eat something, you add more of that ratio of carbon into your body. Now, this carbon-14 is radioactive. It has a half-life of something like 8,000 years, I think. So it is constantly breaking down and turning into nitrogen. So the carbon-14, the way it breaks down is it shoots out a beta particle and it becomes nitrogen-14, which is much more stable than carbon-14, okay? So over time, some of the carbons in your body or in the plant body, whatever, they will change from carbon-14 to nitrogen-14, but you are also constantly replacing them by eating more carbon. So over time, most living things have a very stable ratio. They don't start, these columns don't shift how much of this type of carbon or this type of carbon are making up their cells. But then the plant or the animal dies. And once you die, you stop respirating. You stop taking in new carbon. Well, that means all of these carbons that are stable, they don't fall apart. They stay there. You still have the same amount of carbon-12 after you die as you did when you died, and you have the same amount of carbon-13, but your carbon-14, which is unstable, will still be breaking down into nitrogen. So if you were to wait one half-life, or 8,000 years, you would have much less carbon-14 than any other normally living thing. So what you can do as a scientist, if you let's say you're out digging and you find a fossil, here's a bone. You dig it out of the ground, and it's an animal, so it's made of carbon. You count up the atoms. I mean, you use a special technique to count the atoms. I'm not saying like you pick them out and put them on a tray or something. There's a way to count carbon atoms. So you count up the carbon 12 and 13, and then you count up the 14. Now, if it used to be 0.1% and now it's 0.05% carbon-14, you've gone to half the original amount. And you would say, oh, that thing died 8,000 years ago. I'm rounding. I don't remember what the actual half-life of carbon-14 is, but you would say it died one half-life ago. This is called carbon dating. And if the thing died within a reasonable amount of time ago, usually when I showed you the graph, this is generally valid for about 5 half-lives. After 5 half-lives, this becomes very, look at the flatness of the curve. There's too much error. It's very hard to make a guess about time if you go beyond about 5 half-lives. So anything that died within the last 40,000 years, let's say, you could do a decent estimate of its age just by measuring the percent of carbon-14 left and comparing it to what it should be, which is the ratio that you see in the air, if that makes sense. Now, carbon will do this. Has carbon-14 relative to other radioisotopes actually has a fairly short half-life. There are other things out there like uranium. There are some uranium isotopes and some plutonium isotopes that have half-lives of like billions of years. And so if you were to pick a rock that had uranium in it, you could look at how much of that uranium still remains and how much of it has decayed, and you could find the age of things that are billions of years old. So one of the ways we measure the age of the Earth, let's say, is we look for the oldest rocks that have ever been created. We measure the amount of uranium still left in them, and from those samples, we are able to come up with an age of the Earth, which I think is about 4.5 billion years, right? Don't quote me on that. You can obviously Google it, but that's based on the idea that all radioactive isotopes break down on this sort of inverse exponential curve, which allows us to add up the remaining atoms and figure out how far back that thing had all of its original atoms. Okay? That's half-life and radiocarbon dating.